All right, we're going to continue talking about chords and arcs. We talked about chords. Actually, we didn't do too much with chords, did we? We kind of did like the radius and the central angle and stuff like that. But we did deal a lot with arcs yesterday. We're going to just take that a little step further today. And we're going to throw some chords in there. So let's talk about chords first. Here's a circle. Let's make it a little bit bigger. Now watch this. What I'm going to do is I'm going to draw a chord. I mean, nothing special. I just go from one point on the circle to the other. Okay, it wasn't in any particular magical place or anything like that. Watch what I'm going to do with this. I'm going to copy and paste. And then I'm going to put this somewhere else. I could put it like right here if I wanted to. It would be parallel, but it doesn't have to be parallel. Let's just, for fun, let's just kind of move it around. So I didn't change the length of it at all. Do you believe me on that? So what I'm going to do is take this and put one end of the chord on one part of the circle. So anyway, both endpoints of that chord are on the circle right there. Everybody see that? Alright, so if I did that, this chord right here cuts off this arc. Let's put some letters in here. Let's call this AB, and let's call this CD. So this chord AB, cuts off arc AB. Everybody see that? This chord CD cuts off arc CD. So, I don't know. Where do you think we're going to go with this? Well, let's look at the arc that it cuts off. If I can... There we go. It's a little squiggly, but you get the idea. Look at that arc right there, and then what? Oh, I'm practicing, don't worry. That's all I do at night. I play ping pong and I come and practice drawing these lines. Alright, so look at the two yellow arcs right there. Any idea? What do you think? Yeah, they're equal arcs. Exactly right. Okay, and they go through a proof. I'm not going to do it right here, but they do go through a proof. Yes, proof. Yeah, let's do it. Let's do the proof real quick. Oh, stop. It's not like you think. Come on, grow up. Have some fun with this. Let's change this color to pink. Okay, now watch what I'm going to do. I think I can prove it. I haven't really researched it that well, but watch. If I did this, and then I did this right here. Okay. Now, what did I start off knowing? I didn't know the arcs were equal, right? I knew the chords were equal. So AB, right, is equal to what? CD. All right. Now look at the things that I drew. Call this X. All right. Look at this right here. Look at AX, BX, CX, and DX. Tell me something about all those. They're all equidistant. Why? Because they're all what of the circle? From the center. Yeah? Give me a word. They're radius, okay? Or they, plural, are the radii of the circle. Would you agree? So what can I do? I can say this and this are equal. This and this are equal. Couldn't I? So what's true? Listen to me. What's true about all both of these triangles right here? Congruent. Right, they're congruent. If they're congruent, what's true about the corresponding parts? Corresponding parts are also what? Congruent. So look at this angle right here. It's opposite this side with one arc, or one tick mark. Everybody see that? Look at this angle right here. It's opposite what? The side with one tick mark. What's true about this angle and this angle right here? They're the same. Okay, well, they're not vertical angles. Now, they're not vertical angles. Okay, because remember, vertical angles are only formed by two lines, two straight lines. These two angles are not formed by two straight lines, are they? All right, so they're not vertical angles, but they are what? They are equal to each other. They are congruent to each other. Do you see that? Because corresponding parts of congruent triangles are congruent, right? CPCTC. Remember that, don't you? Bring back good memories? No. Okay. So this angle is equal to this angle. Now, what is this angle? This angle is formed, or the vertex of the angle is at the center of the circle. So what kind of a name do we call this angle right here? This is a central angle, right? We talked about this yesterday. This is a central angle. What's true about the central angle? The central angle is equal to what? Its arc. So whatever angle this is, this arc is going to be the same degree measure, isn't it? Okay? Well, look. This angle right here is the same as this. So what do you think? So both of those arcs have to be the same. If these two angles are equal, right, then these two arcs must be what? Equal to each other. And there's your proof. That's a proof right there. Okay, we just proved it. Isn't that cool? That wasn't so bad, was it? So I just proved to you that arc AB and arc CD, sorry, let's write it like this. Arc AB is equal to or congruent to arc CD. Okay? There you go. That was nice, wasn't it? All right, let's do, let's see, do we have time? Yeah, we have time. Let's do a quick little example here. All right, this is just a little bit of a twist on that last thing that we did. Okay, basically, here's a short way to say this. That if I have a circle, if I have one circle, equal chords have equal arcs. You hear me on that? So if I have two chords in one circle that are equal to each other, I'm sorry, yeah, that's right. If I have two chords that are equal to each other, then their arcs are going to be equal to each other. So equal chords have equal arcs. You with me? It works the other way too. Equal what? Arcs have equal chords. So if I didn't know this chord right here, AB, if I didn't know that, but I did know that arc AB equals arc CD, then what could you say about the line that connects those? They would be equal as well, okay? That makes sense, doesn't it? That's the converse. We've been doing that all year, haven't we? But here's another, it's just a little bit of a twist on this. This is one circle with two arcs in the same circle. Okay, so what I'm doing right here is this. I'm going to take two circles, okay? There's an arc, and what am I going to do? I'm going to copy and paste it, and let's just rotate it just to show you that it doesn't have to be facing in the same exact direction. I mean, it could be, but I don't know, So where's this going to go? About right. Let's do it down here just to make it look a little different. Okay? Alright, so what was I given? I was given that this chord equals this chord right here. Alright? We'll call this W, X, and Y, and Z. This is a little bit different, but kind of the same, isn't it? It's different because we're doing two triangles, but we still have two arcs, but we have two what did I say, triangles? I meant circles. We have two circles, and then we have two chords right here. Everybody with me? So before we just had one circle, didn't we? We had two chords in one circle. Now we have one chord in two circles. So anyway, this is equal to this. What do you think is true about arc WX and arc YZ? They're going to be equal to each other as well. Okay? And I don't have to go through that, but that's that. Are we okay with that part? All right. So you can have one circle with two equal chords in it, all right, and those two arcs are going to be equal. You could have two, actually, they have to be congruent circles. Let me just double check on that. Where is that theorem? I don't even know where the theorem is. Yeah, it's got to be congruent circles. It's the first theorem in the book, okay? So these circles have to be congruent, which means what has to be true about the radius of this. They got to be equal to each other, okay? You could do the proof with that too, since you know they're congruent circles. You could put the radius here, 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 here. Do the same thing with congruent triangles, just like we did before, okay? So I'm not going to go through that again. Let's do, let's change gears just a little bit. Actually, let's do this. Look at time. No, we're not going to do that example. That's too easy. It's almost a waste of time. Let's go to the next theorem right here. And, oops, let me grab a circle before I do that. Copy it. Alright, there you go. And here's a circle. Here's another theorem that we're going to do. Let's make a straight line out of it. I'm not going to do the example. Let's see. It says if a diameter of a circle is perpendicular to its chord and it bisects. Okay, cool. This is a good, interesting one. What I'm going to do is draw a diameter right there. It doesn't necessarily have to be like horizontal looking like that one. It just happens to be. All right. And watch this. If I have a diameter that intersects a chord, I could draw. I'm sorry. It's not just intersects, but it's perpendicular to a chord. So if I start here and do here. Now, what's the if part? What did I say was true? I said if that diameter was what to that chord? Not just intersects, but does what? Perpendicular, right. I said perpendicular. So this is what's given. All right, so I know this. They tell you that this diameter is perpendicular to this chord right here. Now, I'm not going to go through the proof on this, but because we're just running out of time. But let's just try to come up with a conclusion, just kind of eyeballing it, because it kind of makes sense, I think. If this is perpendicular to this diameter is perpendicular to this chord right here, how do you think it hits that chord? Here, we'll call this AB. That's right. It bisects the chord. Exactly right. Do you see that? It looks like it does, doesn't it? And it does. And we could probably draw some triangles and that kind of thing for the proof. I'd have to think a little bit about it. I don't know that proof off the top of my head, so I'm not just going to try to sit here and waste time and figure it out. But you probably could prove it. So what you would come up with is that this, we'll call this C, if this is perpendicular to this chord, this diameter is perpendicular to the chord, then this segment AC is going to equal this segment BC. So what does that mean? That perpendicular is a bisector too, isn't it? Okay, so it bisects that big arc AB. So we know that AC, line segment AC, equals line segment BC. When is that true? It's only true when the diameter is what to the chord? Not just intersects it, but what? It's perpendicular to it. Okay, because watch. What if it, let me just kind of show you. What if it was not perpendicular? That chord was not perpendicular. Is it even remotely close to bisecting that chord? No. So it's only going to bisect it if what? That chord is what? Perpendicular, right, to that diameter. Make sense? Okay. What else do you think it does? There's also something else here. There's an arc, isn't there? Okay. Yeah, there's an arc. That AB right here, we'll call this D. So look at arc AB. Where do you think this hits arc AB? Okay. At the, yeah, at this, I don't even know what you would call it. Would you call it a midpoint of an arc? I'm not really sure, to tell you the truth. But it bisects the arc. We do know that, okay? So this diameter bisects arc AB. So that means that arc AD is equal to what? Arc, yeah, DB, or I'll call it, why did I put an A there? BD. Alright? So it does two things. So this and this is bisected as well. Alright, so if a diameter is perpendicular to a chord, then it bisects two things. It bisects the chord, and it bisects that arc. Alright, that's going to be very helpful, because they're going to give you some stuff. They're going to give you some angles and things like that. Here's a little hint. If they give you some angles and stuff like that, a lot of times you're going to want to draw a triangle out of this. And so look, you've got a triangle and all that kind of stuff. Sometimes that's very helpful. Sometimes you want to do this. Just depends on the problem, right? Just to make triangles out of it, because it's not just any old triangle. What kind of a triangle is it? Well, it's a right triangle, isn't it? Okay, so you know a lot of stuff about right triangles and things like that, so that could be helpful. I'm just not giving you an example right now, but I'm just saying that this could be helpful to you. So think about that. You know, they might give you an arc and say, okay, what's a certain angle? And you're like, well, I don't know. I don't see any lines there. I don't even see that angle. So what do? You draw the line to make an angle, and then you can solve for stuff. All right, so that's just a little helpful hint to you when they give you some of these problems. Let's do that a little bit again. Watch this. What if I knew that, let's see. Let me see what it says. Sorry. Perpendicular bisector chord is the diameter of the circle. Okay. If I have a chord, watch this. If I have a chord and then I have a line, looks very close to the same thing, all right, but the if and the then are different. This one right here, it doesn't say that this is a diameter, all right? We don't know that it's a diameter. Like if I wanted to get rid of that circle, that center right there, tell you what, let's see if I can get rid of that little dot, yeah. Okay, so let's say this, and I don't know that it went through the center, okay? I'm not really sure, because I don't see the center there, and I don't see that it went through there. But what if I knew this? What if I knew that those two were equal to each other, okay? And if I knew that this arc was equal to this arc right here, what do you think you could say about this line right here? What do you think that line is if this stuff is true? Let's see, the perpendicular, let's see. I guess I should say this. I need to say this. I'm sorry. The perpendicular bisector of a chord. Yes. All right. So what could I say about this line right here? We'll call it AB. What could I say about line AB if I'm given that this stuff is true? Travis, what do you think?
If it bisects the two arcs and two chords.
Well, but I'm given that. It's given. So I already know. I already know that this thing bisects this chord and it bisects that arc. I know that already. So what do you think, Rachel? What do you think I could say about AB? What is AB? It's a diameter. That's right. Okay, I didn't know it was a diameter to begin with. Okay, but if it is perpendicular and it bisects this right here, then I know it's a diameter. It could also be something else. What else could it possibly be? It could be about right there. It could be a what? It could be a radius as well, couldn't it? All right. So that could be a radius as well. Does it make sense? All right. So it's a little different. It's just kind of flip-flopped a little bit there. All right. Let's see what else we got. All right. This one might be a little tricky to draw. I haven't tried this on this program yet, but let's see. What if I said, I'm just going to draw some distance from here to here. All right. It's from the center. It's just some arbitrary distance. It's not the radius, is it? Because it doesn't go all the way to the circle. It's not a diameter. It's not even a chord. It's just a distance from the center. All right. I'm going to take that. I'm going to copy that. And just for fun, let's just rotate it a little bit just to make it look a little different. Okay. And what if I said, I'll tell you what, let's rotate it a little bit more just to kind of get it out of the way. Let's say I rotated it like this. All right. Now, what's true about those two distances that I drew? I copied and pasted, so guess what? They're what? They're equal to each other, aren't they? So that little segment and this little segment, Chandler, you getting all this? This little segment, Nico, this little segment and this little segment are equal to each other. What if I did this? This is going to be a little bit challenging, but let's do this in a different color. Let's go this color. Watch. What if I made... This is going to be kind of tough. See if I can do it. Alright. Let's see. Alright, that's not bad. Actually, it really didn't... Yeah. I'm going to do it like that because I want it to be perpendicular. Alright. So what I'm doing is this. I just found the distance from the center to that chord. Remember we talked about the distance from a point to a line? Remember if I had a point and a line, what's the distance from that point to this line? Is it like from here to here? No, where is it? It's what? It's perpendicular. So the distance from this point right here, the center, to this chord, if it's perpendicular, that's the distance from the center to the chord, okay? Everybody find that? So, watch this. Let me try to draw this again. I probably should have put that distance somewhere else, but I'm going to try my best to get this right from there to there. Alright. Cool. So look, this is the distance from the point to this chord. This right here, this little white line right here, is the distance from the center to this chord. Watch, if these two distances are equal to each other, what might your guess be about this line, or this chord and that chord right there? They're what? They're equal to each other, exactly right, okay? And they will be equal to each other. Alright, so if the distances are equal, then the chords are equal. Alright? So what if the chords started off equal? What do you think would be true about the distance to the center? Then the distances are equal. It goes both ways. Right? So if the distance is equal, then the chords are equal. If the chords are the same, then the distance from that chord to the center are going to be the same as well. Alright? It's a lot of stuff. It's a lot of stuff to keep straight. So you're going to have to review it. Alright? Look at your notes. Review this video again. And just make sure that you stay up on this, because it's not as easy as you think to remember all this stuff. Do we have time? We have time. Let's do it a quick example, okay? Alright, here's an example in the book. It actually ends up being a really easy problem. It's just you got to know the relationships, okay, and what's going on. So look what we have right here. From A to B is the distance, isn't it? From this point to this chord. And from A to C is the distance, okay, from this chord right here. And here's what they tell you. They say that Wx, this is given, okay? They tell you this in the problem. Wx equals xy, which equals 22, all right? And it says find AB. And they tell you a couple other things, too, I need to write down. Let's do that in a different color. Let's go green. They tell you that this right here, AB, is 5x. And they also tell you that this is 3x plus 4. All right? And they tell you that Wx right here. You see this whole thing, and this whole thing is 22. Actually, it doesn't even matter if it's 22. All we care about is that those two chords are equal to each other. So watch. If the two chords are equal to each other, what must be true about the distance from that point to that chord, from the center to the chord? It's got to be equal, right? So I don't really care that it's 22. That's really not going to help me. This is important, though. Okay, without knowing that, if I didn't know that those two chords are equal to each other, I would not know that these two distances are equal to each other. Does that make sense? Okay, so if the two chords are equal, these two distances are equal. So really, the math is very, very simple. It's just understanding that these two are equal to each other. All right? I don't know. Maybe they put that 22 in there because they're probably thinking, you know, maybe the kids will put 5x equals 22 or 3x plus 4 equals 22. I don't know. Actually, it would work out anyway. Because they're both equal to the same thing, so it actually, I think it would work anyway. I think. I don't know. Well, anyway, let's do this. Let's just set these equal. So this and this have to be equal to each other. That's easy. That's just baby stuff. You can do that in your head, can't you? Minus 2x, then divide by 2. So what's x? It's 2. All right. Oh, they say find AB, don't they? All right. So that's easy. What is AB? It's 10. 5 times 2. Don't forget to plug it back in, right? So AB is equal to 10. All right. Without doing any math at all, what's AC? It's 10. Okay. Tell you what, they tell you WX. Yeah, we'll just stop right there. That's good enough. All right. So it shouldn't be too hard. The math is probably not going to be the difficult part. It's understanding what you set equal to each other and all that kind of stuff. That relationship between all those segments. Okay. Let me put some problems up here. I don't want you to go away empty-handed. So this is section 10.3. And we're going to do pages 705, 706. See, I'm even, I told my 7th period honors class that they had to watch this video, so they still have the homework too, even though we're not having class today. Isn't that mean of me? It is. I'm such a mean teacher. There you go. All right, 7 to 23. You get to skip a few in between there, and then go 31 to 33. All right, have a good weekend.